Hi, everyone. Thanks, Sid, for that lovely introduction. So I'm actually going to be talking about a paper that was work that I did with Sid, as well as Alistair Fletcher from the University of York and Janet Actas, also from the University of Bristol. So if you don't listen any further than this, all you really need to know is that any two users that want to communicate using quantum key distribution need a pre-shared key. That's because of a process called authentication, which I'm going to discuss. This normally in QKD work, it's just considered as a non-issue, but it's a major concern actually in terms of resource requirements and the security in large networks, both for industrial providers of QKD and for the government. We're going to discuss how this can be minimized using trusted third parties, and then we're going to combine it with a pre-existing protocol called quantum flooding. So I'm going to start by introducing authentication, discussing how we're going to use a third party. I'm going to use some data which is from a previous experiment at Bristol, actually an 8-user network, quantum network experiment. And we're going to talk about the security and scalability implications of that. I'm going to introduce flooding and then our slightly modified protocol, which we're going to call quantum secure flooding. And then we're going to apply that to a particular example. So in any QKD protocol, you have to have classical communication. For example, in BB84, you need to send information about the measurement basis. This is normally, assumed to be public, as in we don't need to assume that it's secure in any way. Otherwise, there really wouldn't be any point of having QKD. But it has to be authentic. So that means, for example, if Alice and Bob are our end users, and Bob sends a message to Alice, Alice needs to know that Bob is the person that sent it and that it says exactly what Bob wanted it to send. If that wasn't the case, then you could have someone intercepting the quantum channel and the classical channel and just sending their own states and their own messages, pretending to be Bob. And that's called an imposter attack, and it's what we want to avoid. So this is normally carried out using the Wegman-Carter scheme, which is a classical scheme. So our two end users, again, Alice and Bob, have some pre-shared key, which I've called K. And then they send a message, which I've called M, and then they generate a tag. So the tag depends on the message and it depends on the pre-shared key. That is, if there was an imposter and they sent their own message, if they changed the message, then they wouldn't be able to work out the correct tag because they didn't know the pre-shared key. And they wouldn't be able to just send the same tag because the message would be changed and therefore the tag would also have to be changed. So there's some inherent insecurity to this scheme, and that's the very slight probability that given a particular message and tag pair, you can guess a different message and tag pair, but that can be made arbitrarily small depending on the length of your pre-shared key and the length of the tag. So some of you may have seen last year, March 2020, the National Cybersecurity Centre released a white paper on QKD, basically saying that they didn't support its use nationally, and authentication was highlighted as one of the major drawbacks of QKD. Partially because it's a reliance on a classical scheme, which is the Wegman-Carter authentication protocol, and also because of this need for a pre-shared key. We also know from industrial partners that manually delivering a secure, unique key, because to ensure it's completely secure, this normally has to be done in person. That's big overhead resource costs, and it's not something they're just particularly keen on. And it just puts people off employing QKD in general. So we're going to get around this, and the way we're going to do that is we're going to introduce a third party. So this is someone we're going to call Chloe, and let's say it's a friend of both Alice and Bob, and that Chloe has the authentication key that they can use, and she sends it to both Alice and Bob. The important thing to mention here is that QKD normally proceeds through rounds. So the aim of QKD is that Alice and Bob end up with their own secret shared key. However, they're going to do that for a certain period of time. They're going to build up their key, and then they're going to stop, and then they're going to start a new round. In that new round, a certain amount of the key that was generated in the previous round is going to be used for authentication. And a certain amount of it is also going to be used, for example, to see if someone was eavesdropping. So the important thing here is that Chloe needs to be trusted in step 1, where she sends the authentication key to Alice and Bob. She also needs to be trusted in step 2, where Alice and Bob carry out that first round of QKD, because during that time, she could easily carry out an imposter attack because she has the knowledge of the authentication key. However, in the second round of QKD, which is step 3 here, assuming that Chloe did not carry out an imposter attack, and therefore that means that she has no knowledge of the secret shared key that was generated in the first round. This is one of the essential assumptions of QKD. So this means that by a trusted third party, what we really mean is a temporarily trusted third party. So let's see how long that temporary trust needs to be. So here we've used rate data from the 8-user experiment carried out at Bristol. Let's say, for example, that Alice and user I, we're going to call Ivan, want to communicate with each other. They have the necessary infrastructure in place. They have a quantum channel, but they don't have a pre-shared key. So they trust this user, Bob, to send the key to both Alice and Ivan. The amount of time that would take and all of the parameters for calculating this are in the paper. You can see here is about 30 minutes. So just to be clear, the bins on the x-axis are the desired end link. For simplicity, we've said it's our new user is I, and they're wishing to communicate with someone on the network. And then the trusted users are the different colors. And it maximizes at about 35 minutes. So that's actually a very reasonable and practical amount of time. For example, if Alice and Bob lived near each other, but Ivan was in a different country, Alice could send a rep over to Bob's lab just for the amount of time taken for her to carry out the first round of QKD with Ivan, make sure Bob's not carrying out an imposter attack. And from that point onwards, she would have a secure channel with Ivan. Now we're going to complicate that a little bit in the case that, for example, it's not easy to find one completely trusted node. And we're going to say they're going to use a network of trusted nodes. In this case, we're using a framework which developed in this paper from 2010, and we're saying there are multiple non-overlapping paths. This is a slightly simplified topology. More complex topologies are discussed in a little more detail in the paper. So we've labeled every path by I and each user in the path by J. And then each of those users we're going to parameterize by some level of trust T. Mathematically, this probably makes the most sense, but I know it maybe feels a bit bizarre that you don't have a personal spreadsheet at home with every single person you know and the percentage that you trust all of them, or like maybe you do, but this is how we're going to mathematically describe it. So for example, Alice could decide that she only has 90% trust in Bob, but she thinks there's a 10% chance he's malicious, so she'd give him a trust value of 0.9. Ivan would also have his own trust in Bob, and he'd have his own different subjective trust value. We want to then work out the probability that a key passing through this network is compromised. By passing through the network, what I mean is, let's say Alice is going to send the pre-shared authentication key to Bob. She's going to send a different key through each of the different non-overlapping paths. Then at the end, Bob is going to bitwise modulo 2 sum them together, that is XOR them together. So a malicious user would need to know the key that passes through every single one of the paths to work out the overall authentication key and therefore be able to carry out an attack. The probability that this can happen is made up of two different terms. So the first one is the fact that is the scenario in which there's a malicious user in every one of the paths, and they're able to send the key they have to all of the other users. They all communicate with each other and they work out the overall key. And then the second term here is the probability that there's a malicious user in every path but one. If those malicious users were sending the key that they had to everybody they knew, then even if someone's completely trusted on the final path, they would receive enough information to work out the overall key, and then we still say that the key is compromised. Obviously, this is itself true in like a classical routing protocol, but we want to bear it in mind later on. So as you can see, multiple paths improves the security because that means there's more keys to XOR at the end, less chance for a malicious user to gather all of the keys. A longer path reduces the security, but that's more likely in a less densely connected network. The final point that I'm going to make on authentication before we move on to flooding is the idea of scalability. So we're going to think about a slightly different scenario and say that you were a service provider and you wanted to initialize a quantum network. You know that it's difficult and expensive to send pre-shared keys, but you know you have to send a certain number of them, or you want to basically ask how many keys need to be shared at the beginning of this network experiment or metropolitan network or whatever. So we're going to use a slightly different framework to consider trust or malicious users. Again, this is taken from the Survey 2010 paper, and it's going to be something called a collective adversary. So we're saying that up to C nodes in the network can be malicious. They can work together to form an adversary that's acting against you, and you don't know who those nodes are. So using the processes that we've described before, in the case of a fully connected network, the number of initial keys that need to be sent out, which is nk, actually scales linearly with your number of users, which is n. This is a pretty good result considering the fact that in a fully connected network, the number of connections actually scales with n squared. And it comes from the fact that if you use trusted parties, as long as you have two secure non-overlapping paths between each end user, then the key is going to remain secure. So for the next part of the talk, I want to move on to flooding. Flooding is originally a classical protocol that sends a message between two end users through a network. So every node in the network is used once. Let's say Alice wants to send a message to Bob, what she does first is she sends a message to every user with whom she has a connection. When they receive that message, they send it again to all of the users that they're connected to, apart from whoever they received the message from, and so on until it reaches the end user. This isn't just to make sure that the message eventually gets to the end user, but actually increases the overall efficiency. You'll notice that the routing protocol itself isn't unique. So for example, in this case, the center line between C and D could be in the opposite direction. So we're working with the quantum flooding protocol, which is an update from the classical protocol introduced by Stefano Pirandello a couple of years ago. So for an example, this is a Sankey diagram showing the movement of keys through our network. Again, this is using rate data from a previous experiment. Our end users here are the users that we've labeled C and D. You can see that they already have a channel between them that's indicated in the light blue. So they send a certain amount of key between each other. But also the user C, Chloe, is able to send a certain amount of key to all of her connections. They pass it on to the final user D, and that increases the efficiency of the communication between them. So here you can see how the key rates improve using flooding. The darker colors are the initial rate that was generated in the experiment, and then the lighter colors are the rates that they would be able to achieve using flooding. This is actually the first experimental demonstration of an increased rate using multipath routing. So we're going to modify this slightly. We're going to introduce something which we've referred to as quantum secure flooding, and that's where we're going to kind of join together these protocols of our secure authentication key transfer and flooding itself. So let's say our end users are again A and B. They're connected by multiple sets of non-overlapping paths. In this case, each path is only going to have one user in it. So those paths are, for example, A, C, B, A, I, B, and so on. There's going to be N users in between them, as indicated by the different colors on the graph. And then what we're going to do is we're going to split all of those users into subsections. So, for example, Bob is going to receive keys from all of those users, and then within each subsection, he's going to XOR together the keys that he's received from the subsection. And then that's going to give him a certain number of keys, which is the same as the number of different subsections there are, and he's going to concatenate them together. That's a little bit complicated, so I'm going to repeat it again. We have a number of non-overlapping paths between Alice and Bob. Those paths are going to be split into subgroups. When Bob receives keys from each subgroup, he's going to XOR them together, and then the overall key from the subgroup is going to be concatenated. So as you can see, there's a trade-off between efficiency and security. Security is increased when you XOR keys together. So the more different subnetworks you have, the better the security. However, efficiency is increased when you concatenate keys. So sorry, I had that the wrong way around. The more subgroups there are, the better the efficiency, and the bigger subgroups there are, the better the security. So you can see that trade-off in this graph. So this is the case where we're saying each of the intermediate users is trusted a certain amount T, as before. We're saying they all have the same trust value in this case. And then we're trying to reach the same overall security of little t. And then, as you can see, as the size of the network increases, actually the rate that we're able to reach and the security we're able to reach increases as well. So this protocol actually works better on bigger networks. I just want to mention as well, the rate is normalized. So we're saying that each individual connection has a rate of 1. And therefore, we can see we can go up to about 40 times the initial rate, which is really great. So now we're going to apply that to example network. Using data, again, that comes from our 8-user experiment. We've got a slightly modified topology here. In the original experiment, it was a fully connected network, but we're going to say that as before, Alice and Ivan are our end users, and they're connected by many different paths that are just made up of one intermediate user. So Alice and Ivan have their subjective trust values in each of those intermediate users. Those are here. And then when we're planning actually the best protocol we're going to follow, they're going to do it based on the lowest trust value. So for example, Dave has been assigned 0.98 by Alice and 0.97 by Ivan. We're going to say that he has the kind of overall trust value of 0.97 because that's a lower one. And then here we find the ideal flooding protocol, slightly simplified because we're just splitting it into 2 groups of 3. That is, in each of these subsections, the key received through this intermediate path, these intermediate paths are going to be XORed together. And then these 2 keys from the 2 different subsections are going to be concatenated. This is the rate that which we were able to achieve, and then this is the trust value that we're able to achieve. And you can see that if you're willing to settle for a slightly lower rate, there's several different ways to achieve that trust value. If you had slightly different initial trust values here, obviously your final trust would be different, whereas the rate data comes directly from the experiment. So to summarize, the main thing that I want you to take away from this is that authentication shouldn't be such a major concern, particularly if you're using trusted third parties. There's a number of different ways that you can do it. Temporarily trusted or partially trusted, you can parameterize the amount of security that your authentication key has. You can also implement quantum secure flooding to make sure that that key remains secure and it is efficiently transferred through the network. There's ongoing work at the moment to consider more complex network topologies. So for example, when we discussed scalability, we're looking only at a fully connected network. And when we looked at quantum secure flooding, we had a very specific topology. So that's being continued at the moment. I'd say thank you to all the collaborators. So Alistair Fletcher, as I said, mainly led the flooding part of it, whereas I worked on the authentication half mostly. Sid is fortunately here as a session chair, and if you have any questions about the experiment itself, he'll be much better qualified to answer them. And then thank you to all the other co-authors and the many, many experimental collaborators. And here's a list of the references I used. Thanks.